Let's take a look at energy. Here are a few crude drawings that I've made for a scenario for us to investigate and look at the energy. For starters, we have scene A, then down here scene B, and then scene C. So these go in order. And we want to talk about where the energy is in each one of these scenes using a pie graph. So let's start with scene A. In scene A, all the energy is gravitational potential energy, and that's because it has a height. And so this is where all the energy is coming from for other things later on. There is no kinetic energy because the person is being dropped from this height and the velocity is 0. There's no elastic energy because there's nothing like a bungee cord or a spring or a trampoline, which you're going to see in the next scene. In scene B, the guy has hit the trampoline and the trampoline has stretched and brought the person to rest. So they have a velocity of 0. We know what's going to happen next. They're going to be sprung back up. But we caught them at this snapshot. So no gravitational potential energy because they are down at ground level. But all this energy has been transferred or converted from gravitational potential energy into elastic energy, into the energy necessary to stretch out this spring. Then I would like to say that there's probably a little bit of energy that has left the system. Dissipated energy. It's not a form of energy, but it's the energy that we don't have in this system anymore. It's left probably as sound and heat due to friction, due to air resistance, and due to the fact that the trampoline material is being stretched out and it heats up a little bit. And so we've lost some energy in this system and it went elsewhere. And that's what we call dissipated energy. Then we go to our final scene. Our final scene, the guy is more than halfway up, so he would have some gravitational potential energy, and I would say a little bit more than half of what he had in the very beginning, because he's not halfway up, he's a little bit more than halfway up. What do you suppose the rest of the energy, where the rest of the energy is? Well, he's not going 0 meters per second, so that means there must be some kinetic energy and a little bit more dissipated energy. So our dissipated energy grew a little bit from scene B to scene C, and that's because, again, there was some more air resistance and those things, and then leaving the final chunk here for kinetic energy. Now, if we didn't have this dissipated energy, if we didn't have air resistance, for example, the guy would be able to go faster. So that's one way to think about it. Let's look at another scenario. This time we're going to use bar graphs for a cart that's going down a hill. The thing is like a roller coaster, basically. The cart comes off the top of the hill, rolls down, and then, unlike a roller coaster, hits this spring and compresses the spring. Let's look at the first scene. We're going to do bar graphs. These are the choices we have for energy: kinetic, gravitational potential, elastic potential energy, and then energy that leaves the system known as dissipated energy. In scene A, all of our energy is stored in 2 places. We know that, first of all, the cart has a height, so that's gravitational potential energy. And I gave it 3 blocks. Then the rest of the energy, we have some other energy stored, or not stored, but being used because it already has a velocity. I chose not to give any dissipated energy because we're starting right now, and we're doing our accounting of energy right at this first A scene. So I'll dissipate energy later on, and it does have to be dissipated because there is friction. So let's go to scene B. Scene B, our cart is halfway down the track, about half as high as it used to be. So because it's half as high, I'm cutting the gravitational potential energy that we had in the beginning in half. So where does that extra gravitational potential energy go? Well, if you've ever rolled down a hill on a roller coaster or rolled down a hill on a bicycle, we know that when you go down a hill, you get to go faster. So now we have more kinetic energy as a result of converting that gravitational potential energy. By going lower in our height, we've converted some of that to kinetic, and so you can see the kinetic has grown. And because there's friction, we're going to have some dissipated energy. And if you look at these blocks, I have 1 block, 2 block, 3 block, 3.5, plus this, 4, and it adds up to the same amount of energy that we had in the beginning. So this is an accounting project. You can't have more energy in scene B than you started with in scene A. Let's look at scene C. In scene C, the cart is no longer moving. Velocity is 0, so we will not have any kinetic energy. In scene C, the cart is at its lowest point, So it's not going to fall anymore. So we will not have any gravitational potential energy. But as you imagine, why is it going at 0 meters per second? Because it was slowed down by this spring. It compressed the spring. So we have some energy dissipated because of friction, and we dissipated a little bit more than we built on to the energy that we lost, and then the rest of the energy is stored up in that spring, because we know that what that spring is going to do. That spring is going to launch that cart back. And so at this snapshot, it's being energy stored as elastic potential energy. There you go. I hope it helps.